So we're going to get more into the dynamics, the faster timescales now, which is more interesting to me in a way, and then leads into all this stuff, all this crazy stuff on like why are they spending billions of dollars on batteries, which just amazes me. Okay, but so last time we led into this. So last time we were looking at a model of just a generator, and unless you're a mechanical engineer, you were bored to death. You basically have fuel, which goes into a turbine. The prime mover, the thing that's spinning around, you know, creating torque on a shaft. And there's a generator that produces electricity. Okay, so we need to understand this a bit because we have to understand what it is that makes the grid operator's job hard. You know, I mean, I don't know about, I know several of you want to get jobs like working in these demand response companies like Enernoc and all that. And that's my big research area. And it's, you know, if I get rich, that'll be why. And what's easy and what's hard. And I think that the biggest, most important thing to understand is like, what are the important dynamics in the grid? And understand the dynamics of the grid, you have to understand the dynamics of the generator. You know, that's really it. In some science fiction future world, when we're all living off of solar and wind and geothermal, this entire course is obsolete, you know, all this stuff. I mean, this part of the course is obsolete. You know, if there aren't any big generators with lots of inertia spinning around, then this is irrelevant. But this is going to be around for a long time, you know. I mean, Florida Power and Light didn't spend $1 billion each on generators thinking they'd only last a few years. So they'll be around for your entire lifetime. So this is chapter 10 of this awful book. I'm sorry, it is. I mean, it is. It's just all the books are bad. And I'll explain what I mean by that. Some of it's great. Some of it's great. And the additions improve each time. Okay, so we saw Newton's laws. That's easy. Okay. So we saw last time that there's a mechanical torque, you know, which is, you know, due to the fact that you've got this turbine pushing. it's my incompetence. His corruption still stands. Okay. All right, so you go through that, and then there's another step. So, because we're trying to get to the dynamics of a generator, and what we don't care about torque and the shaft speed. We care about the grid frequency and power. And so what we do is we say that, again, what is it again? Energy is force times distance. Okay? Energy per second is force times speed. All right? And so here we've got force, torque, and we multiply by rotational speed, and we get power. And yeah, and I better be careful. Well, yeah, I'll put theta dot there. Put it like that. So the power, you know, it's the torque times the speed, and the speed is the grid frequency divided by the number of pole pairs in the generator. And the immediate approximation you make is this, that the grid frequency is 60 hertz. Because remember we talked about how it's 1% error, you know, we're talking about. So you make this approximation right away in these equations. You know, just pretend that's true. So when you do that, you take this and multiply it through by omega naught, and you get, and the same with P. All right. So we take this equation, and all the 1 over p's drop out. But I'll put them in anyway. So what did I get? I said that theta dot is 1 over p omega, so theta double dot is 1 over p times omega dot. And then the right-hand side, I get a 1 over p blah, blah, blah over here. What's that? Right over here. So 1 over, yeah. So, but anyway, so I'm just writing down Newton's laws again, but I've multiplied through by omega naught, and blah, blah, blah. Multiply through by omega naught and use these correspondences. I feel like that, yeah. Did I miss something? Wait a second. If I multiply through by omega naught, and I have to divide by p, let me just write it down, and then we'll fight about it. The p's all have to drop out in the end. They have to. And so it's just plugging in these equations when I multiply through. And yeah, because of the fact that I'm multiplying by theta dot, and I have to place that by omega over p. So that is correct. So the p's all cancel out, so it was okay there. So when I called this m last time. So this is what you would naturally get from this. So that's what I had. But then I did a little sneaky thing. I threw in another term. And that's question 1. I said, this is an approximation because of loads and stuff. I realized that's ridiculous. I can be more precise. I'll be more precise. Some things that are easy and important I should fill in. So today I've got to explain this extra term. How would I go from this to get this? What has to do with this, I'm really being a bit imprecise about this. I'll just put a little prime there. Because to go from here to here, you have to change the definition of this extra term. Okay? It has to do with the fact that PE is determined by the load. So the torque's dependent on the load. PE is the amount of power being absorbed by the loads. And some of those loads are frequency dependent. All right, so we'll go through that. So that's question 1. So question 1 is that we have to address. Question 2 is how do we control this monster? There's the local control. How does a generator try to control itself? And then there's the global control. How does a balancing authority control a collection of generators to make sure that we keep the frequency within 1% of the nominal, the desired frequency, And so this, of course, will start today, but it's going to take a few lectures to go through. And based on the survey, where 90% of you said you knew nothing about control, next lecture, I know I can do it. I've done it before. In 1 hour, you will know all about PI control. We really need it. And we need it. PI control comes up for the local generator, and it also comes up for the grid operator's problem. How the grid operator makes decisions about ramping up and down generators. So, all right. So let's take care of question 1. It's not too bad, and it brings up some interesting issues. It's okay. You with me? All right. So this can go. Yeah. Okay, and again, I'm following the textbook almost exactly. So in the latest edition, it's chapter 10, I said, and so I'll copy my notes for you all, but it's right out of the book, except for some of my editorializing. So the power consumption, the PE is really, again, from the power consumed by the loads. And let's decompose it into 2 parts, one that's dependent on frequency and one that's not. And the prime example is motors. Motors depend on frequency. And so the the NF is not frequency dependent, So and by frequency, I mean the grid frequency, omega of t. And this is really interesting. So, I mean, I've always known this is important, but, motors, do you have a motor in your house, in your apartment? You do. You've got your fridge, all right? Well, a refrigerator today does not count, okay? So, a motor which is directly connected to the grid, plugs in and connected, yes. But the thing is that an example here is a modern refrigerator with solid-state electronics, Same thing is true of fans, you know. So you take a fan and plug it in, an old-fashioned fan with a wire protection to keep you from getting your fingers hurt. That's over here, you know. It'll consume more power if the frequency goes up, you know. It'll spin faster and all that. But now a lot of fans, to make them more controllable, have solid-state electronics, which completely insulate them from the grid, and so they don't give a damn what the frequency is. You know, they'll go from AC to DC and onwards. And so I mean, I've known this, but I didn't realize how important it was until my first time I went to a Power Energy Systems meeting, and this was actually only 3 years ago in Detroit. And it was really funny. There was a big industry discussion, and there was an angry old power engineer who was yelling about the loss of service from. So we're going to find this D here comes from these loads. You know, these frequency-dependent loads. And the fact that we've moved to solid-state electronics with our fans and refrigerators means that we've made D smaller, because we've created this insulation with solid-state electronics. And so this old power engineer was saying, you know, what the WTF, you know, why is it that we allowed them to do this to us? We could have mandated that the power electronics in these motors, in these refrigerators, mimicked old-fashioned refrigerators. And it would have been so cool. It would have made the grid so much more reliable. And he actually punched his fist down and said, why? Why? And he said, because we didn't ask for it. And, and I never got his name. You know, I love this guy. I've been fascinated ever since, you know. So anyway, so with a motor, though, you know, you have basically an approximately linear relationship. And by the way, this is all true, all okay. But at some point, we should have done this. I should have changed my notes, because before I go on over here, all these linear equations, Newton's laws are linear. We're not going to think about Einstein. But a lot of things are not linear, like the things I'm talking about here. They're highly nonlinear effects. And so it's really smart not to look at absolute frequency, but deviation. And the derivative of a constant is 0. So you can slip in deltas everywhere here. And nothing changes, and it's only important right there, okay? Because you know, we're going to get a linear relationship with the deviations, but not overall. You know, so it's much better to write this in terms of deviations. Right? So for these guys, you're going to find that the power, again, when the frequency goes up, the power goes up, and that D is just that proportionality constant. You know? Now, when I said last lecture that D is sort of a fictitious object, what I mean by is that every load is going to have a different D, you know? Now, the grid frequency is the same overall. So what D is an average, a weighted average over all loads, you know? And that's really what's going on. So there's an aggregate response from all the loads, you know, and this would be then an average, you know, or the sum of all the D's, or you know, over all the loads. Okay, would have to be an average somehow. Well, actually, summing both sides. This is constant. It's a sum. Jesus Christ. It's actually a sum. Yeah, the D for each load would be very, very tiny. This is the aggregate change over all the loads. So you sum both sides. This is a sum over all loads. Yeah. You know, so it's n's very large. In the old days when you had 100 million refrigerators, old-fashioned refrigerators, each DI for that fridge was tiny, tiny, tiny. But you sum them all up, you get a reasonable number. Okay, that's the thing. All right. And again, the relationship's very, very nonlinear. You only have a linear relationship approximation because delta omega is so small. All right, so it's really important that you throw that delta in. All right, you with me? I see some yawns. Okay. All right, so you plug that back in and you get the equation I promised. All right, you basically, I'll do that for you. So. What happened to this? So then if you go back here and you plug this in, and this doesn't change a thing. You know, putting in deviations is the same thing. You get that this, first of all, you get that this is equal to the d omega you know, just plug this back in, and then plug this into this equation, and you get this. So okay, take that equation, and plug it in, and you get exactly this equation. And so it answers Q1. It just says that what I called delta PE before is just deviations in the loads that are not are frequency independent. Clear? Done. Yeah. Move on. Yes.
Can you talk about how they're frequency dependent?
Oh, you mean from an electrical engineering perspective, that when you crank up the frequency in a motor, it spins faster, and so it's drawing more power because of that. Yeah. I mean, you can think about it physically. The actual detailed mechanics, I don't know. You know, it's beyond my background, but you can sure imagine it. If the frequency doubled, which it doesn't, you're getting twice as much wind in your face. That's more energy that's required to do that. You know, but in terms of actually getting to the details of the, I'd have to look at the equations of the motor in detail. But intuitively, it's clear, right? Yeah. But that's the thing. So it really is a fact that the D of the grid has dropped in the last years significantly. And that's because of the loads going solid state, and because of generation changing as well. There's a lot less inertia in the big spinning machines as well. So that's causing problems. And if you saw the email I announced about, there's panics about something called droop all the time, and that's what we talk about for the next few lectures. Part of it has to do with that fact. That because the dynamics of the grid are changing, grid operators are insecure about what's going to happen next. You know, because they've got a new system to deal with. You know, it's just you know, if you're not used to driving a Ferrari, it can be scary. You know, that's the thing. You're a very responsive car. That's what happens. I mean, if D is not there, it's a more responsive car in a sense, and that's one part of it. Well, that's I mean, there's two parts: D and also M. The fact that M can be smaller is a big deal as well. All right. So I can kill all this. Now in the book, they actually have some discussion on one more dynamics. Now, you look at that, you have to laugh. I mean, the steam valve, the dynamics between the steam valve and the power, but you know, nobody really cares about this. So they give a transfer function for this. They come up with a time constant called TCH. They're not doing this because they think you care or that they care. It's just they want to emphasize there's a control variable here. And you're not just magically changing power. There's something you're doing. You're either adjusting a fuel valve or somehow a steam valve or the fuel supply rate to the device or something. There's something here which I'm as a control person, I'm going to call that U. The deviation in the steam valve or whatever it is. It's a thing I adjust to make the power go up or down. You know? And this particular form is just chosen so that when s equals 0, you get 1. You know, and I'll come back to that later. All right. Yep.
So that should be D prime. The last one, D prime equal to.
Oh, I see. Yeah. The pre-prime. Thank you. Yeah, that's what I meant. Yep. In this equation, it's it's deviation in non-frequency sensitive loads. That comes up. Yeah. Probably. Yeah, thank you. 2 typos.
Is it a positive that they're moving toward D is decreasing based on what they want?
Isn't that funny? That's a good question. You know, I mean, I've been puzzling about this myself. You know, I mean. Let's. I mean, yeah. Let me say something about that. Wait, what time is it? What time is it? My watch is not set right. 2:25. Okay. Let's write down the fill block diagram and try to answer that question. Because I think I actually, this will be, your question is relevant for sure. Where'd it go? I'll just call it delta, well, I'll do it like that. I think that's right. Okay, so if I took Laplace transforms of this equation, I would get an S times ms here, and I'd get a d there. And I would divide through, and I'd get the difference here divided by that polynomial. So that's why I have a transfer function here, 1 over Sm plus d. And I'm taking the difference of these two terms because I've got a difference of these two terms here. So that's a linear systems description of this. And you know, forget these dynamics. I doubt they're really crucial to anything. These are more crucial. And if you look at like a Bode plot, of the magnitude of this guy here, And this is something you all should know really well. So this thing here has a pole when S equals minus d over m. And so there's a coordinate frequency right there. Yeah. Okay. So this is why I think next lecture I'm really going to have to go and review some control theory. Uncertainty of this value is scary as hell. As a control engineer, uncertainty is scary. Also, if this is small, I'm scared as well. So m being too big or d being too small means that this thing comes over here. And it means that I'm going to have to think about control differently, you know. And so there's a correspondence. This is called the bandwidth. Of this open loop system. Now, I mean, ignoring, of course, this thing here. Let's just assume we can. I mean, God, if this thing plays a serious role, you need to build a better system for controlling your valves. So forget this. So now, if this turned out to be, so what is bandwidth important about? It's about disturbance rejection. If a shock comes to the grid, I want to respond. And if the disturbances are out here in this frequency range, I'm going to have to increase the bandwidth of the closed loop system. I'll review that next time. Okay? If they're not, it's a lot. Then I have a different control strategy. If the disturbances are here, I have to reject them. I have a totally different control strategy than if the disturbances are here. So D getting smaller, reducing the bandwidth of the generators, and also therefore the entire grid, will completely change the way you think about control. Yeah. So D small or actually M big scares the hell out of me. Yeah. And we'll make that clear over the next lectures. Yeah. Okay? Yeah. All right. So we've got this wonderful thing here. And when I see a block diagram, I want to control it. And here we come to a place in the text where it's really, really hard to read in a sense. I mean, I guess it is section 10.4, I think it is. Now, anyway, when chapter 10, you can find it. I think it's section 10.4, and it's really good to get into the mindset of things. To first look at the case of a single generator in an island, and it's called. I mean, I won't give you the language. An isolated generator. There's a term for this, but forget it. It's such a rare thing that you wouldn't think about this much. And here's the architecture of it trying to keep a steady frequency. So we've got our prime mover. And we'd have a tachometer, just measuring the speed. And we want to regulate that speed. So what do? Use error feedback. And I'm going to put everything in terms of deviations, you know. So it's possible that for some reason you want to make the frequency different than the nominal 60 hertz. You know, so maybe this is typically 0. I mean, but maybe sometimes you don't. I mean, in an island, maybe you decide to go to 59 hertz for some reason. Turn everybody's fans down. Okay, so now here's the thing. You'll find this in every textbook. They assume a control architecture off the top. They go through. They put this through a gain. called K sub G. And then they integrate this error signal. Okay, so this is typically 0. So you're taking the deviation frequency, multiply it by a negative gain. The kg will be positive. And then you integrate that error, and you take that as your input U to the system. All right. So U is that steam valve in one case, but whatever it is that manipulates this thing up and down. And there you have it. Now, if you've had a control course, 1, 2, 3, 4. I know it's only a few of you, you gasp. What kind of controller is this? What? Well, I heard PI.
It's also closed.
What?
It's also closed.
Well, it's a closed-loop control, but the specific architecture is PI. But it's not PI, it's I. And nobody teaches I control in a course, I mean, so to completely jump to this architecture like that is a bit eccentric, But it's not this textbook. It's every book assumes an I architecture, where you just integrate the error and you're done. All right? Okay. So it's PI control, but no proportional gain. All right. Well, I want to say a few things about this. So, I mean, I can kill. Well, yeah, I don't need this. We'll definitely need this. We'll come back to this for sure later on. Not today, of course. Now, the typical PI compensator is this. I mean, the typical control architecture. You've got a plant, that's the prime mover that I just erased. And you've got measurements, in this case it's the deviation in frequency. You take them back and you take the difference between what you want the measurements to be and what they are, and you get an error signal. And you put the error signal through a filter, which you design, and that gives you the input to the plant. All right? So a PI controller in general is to take G sub C to be equal to an integral in the frequency domain. So you've got a gain times 1 over S. That means integration. And then just a static gain as well. So in the time domain, I can write this out, right? I've got U of t is equal to, well, 1 over S is integration, so Ki times an integral. Right. So these are exactly identical with the K sub p equals 0. And just look at pattern recognition. You know, you're taking the error signal E. You've got a minus sign there. That's minus E. Sorry. It's wait a second. Wait, what I want, I've got minus signs here. I've got what I measured minus what I want. And over here it's what I want minus what I what I'm measuring. So there's sign inversions all over the place. So that's minus E over here, and that's why I multiply it by a minus sign here. All right? So I get exactly that. Now, the only time you set k equal to 0 is if you're really conservative as hell. You know, in control, you just don't do that. This is really important for stability. But if you've got a very, very low gain, then that's okay. And typically what happens in power is you're really conservative. There's so much uncertainty about dynamics, you tend to be conservative. And that's the reason why they jumped to this architecture. Right? Do you all know why you would do this? It's something you can say in 10 seconds. Well, it's easy to look at this. So a PI controller, the time domain way of thinking about this is that I'm defining U dot. Well, first of all, you can see here, if you have a persistent error, the control will get bigger and bigger and bigger and bigger. It means you're going to push it back, you know, until something happens. All right, that sounds scary. You push and push and push. Maybe you're pushing too hard, something will break. But forget that. Suppose you design this carefully so it's stable. You know, suppose it's stable. Suppose that after a fault or something, suppose that E of t converges to something, E infinity. E dot of t goes to 0. U dot of t equals to 0. I'm just imagining, so there's been a disturbance to the grid, and now I'm watching what happens, you know. And stability would mean that everything goes to a constant and all the derivatives go to 0. Well, look at this equation. You know, U dot's going to 0, E dot's going to 0. As long as Ki is positive, E goes to 0. So it's sort of brain dead. As soon as you throw in an integrator, you know that you're going to get asymptotic recovery. And so your area is going to go to 0. So it's a beautiful thing. So control people are almost excited about this fact as economists are about the fact that we're all going to reach nirvana if we just believe in prices coming from God. I mean, but it is a beautiful fact, and this is not a good way of saying it. You know, there's a much more elegant way of explaining why integral control is good, and I will give a short tutorial next lecture. Okay. The thing is that this is ridiculous. I mean, this is completely for a single small island and one generator. Otherwise, none of this makes any sense at all. All right? And so we won't talk about this at all. It's a good starting point. And the way you would design KG would be based on the dynamics here. And actually, maybe we will do that as a homework problem. You know, how you would choose KG this is stable. I think it would be worthwhile, and it requires understanding the constants here. All right, so we're almost out of time, aren't we? Not quite. Okay, so here. Okay, so now we leave the island and we have a generator in Florida or Pennsylvania or California. It's connected to the grid and it is fixed onto that grid frequency exactly. Can you see how ridiculous this is? You know, delta omega, it might be measured at the tachometer, but it is a function of the entire grid. It's a system property, you know. You can't use this analysis. It's like this is something that's common to all of PJM, you know, all of the US. When you look at what changes, the phase changes over the grid. but the frequency is just fixed, you know. It might not be 60 hertz, but whatever it is, it's fixed. And so this whole thing doesn't make any sense, you know. I mean, take a look. The error is a system property. I can't control it. I can make myself match the system frequency. Well, I've done that. I mean, that's a fact. You can't even think this way. And it really is a challenge to even think about this if you've taken a lot of control, because you're used to thinking about this block diagram, but now you can't think about this in isolation. You know, again, delta omega is not something I can control with my single generator. There's 100 generators, and all of them together affect it. So it's really confusing. So what's done is, first of all, you cannot have integral control. No way you can integrate the error. There's weird jargon in power systems about hunting and generators fighting each other. Forget all that. It's just obvious. If this is a system-wide property, you know, you can't pretend you can control it alone. So all the notions of integral control fall out the window. You just can't think that way. So with the way my yellow chalk, no, I don't have it. So that you make two changes. So you stabilize this thing. So the problem is that integration is an unstable operation. So you stabilize this thing by putting in another control loop. And two, you give the grid up, the balancing authority something to play with. So I've got a feedback loop here. R is something that's positive. This is going to stabilize this thing so that with the persistent error, this won't blow up. You know? R is going to be some small number, and this is going to be from the balancing authority. And this, you know, it's a control problem. It's really interesting. I mean, I've got a problem where I can do things locally to some extent, but you need some God to coordinate globally. Because of the fact that that's a system-wide property, you need a benevolent dictator, a real one, balancing authority, to try to restore frequency if something happens. You know? So I think it's really kind of, even though this is all old stuff, it's fascinating to think about how you would analyze these things. You know, the entire grid and how to stabilize it. So you will understand by the end of October. It'll all be clear. Okay, so until then, I'll turn this off.